Oh, got a great turnout tonight. So welcome everyone to the October 2025 meeting of the Mornington Peninsula Astronomical Society. As usual, my name's Peter, and I'll first of all start off showing some of the things that happened in the last month. The first one in the top left on the screen there, unless you've been living under a rock, we had Taylor Swift put out her new album and had over 1 billion accesses, in other words views and listenings, in the first couple of days, so I thought I'd put up a mention of the star. Move across to the second one at the top there with the rocket looking sounding rocket. RMIT launched this actually a couple of years ago. It got up to 257 kilometres, so it didn't get up to low Earth orbit, but it was well and truly past the point where outer space is taken to begin. And on board they had some Bacillus subtilis spores, which are gut bacteria, and they were testing it for potential use in travelling to Mars and travelling to the Moon, but I think more for Mars. So at RMIT, this is Gail Isles and Eleanor Ivanosa on that particular project, and the rocket was to test how hardy the spores were to going up. So believe it or not, it hadn't been tested before. So they got 13 Gs of acceleration pulled on them at liftoff, microgravity at the top when they're up at 257 kilometres, and then up to 30 Gs as it came back down to Earth. So quite a very high acceleration rates there, certainly more than enough to kill a human. And also it was spinning as it came down as well, about just under 40 revolutions per minute. And they actually showed that the microbe is totally resistant to those, so they were very, very happy with that outcome, because they're looking at potential impacts on astronauts for prolonged flights and also on Mars, and what can actually go out there. Top right hand side there, NASA has actually confirmed where the Artemis landing site will be. It's actually at the south pole of the Moon, in the Aitken Basin, which is the largest basin on the Moon, largest impact crater on the Moon by far. And by extremely good chance, they picked the southern side of that impact crater, and a paper that was just recently published in Nature indicated that the impactor that came in from space and struck the Moon to form that basin came from the north. So in other words, it came in and splashed the material out to the southern end. It would have dug deep into the mantle of the Moon. And so where they've actually picked to land by good chance is going to be where there's probably going to be a lot of the mantle of the Moon at that time has been piled up on the southern side of the impact basin. So these are massive craters, right? You're not talking about something the size of Port Phillip Bay. It's much larger than that. Down in the middle left-hand side there, in Western Australia, the new Norcia 3 antenna has been built, but it's not fully commissioned yet. It's a new 35-metre radio telescope that the European Space Agency has commissioned as part of their deep space network. Most of you here may have heard of Tidbinbilla in Canberra, where NASA has their deep space tracking network, where the European Space Agency has their own as well. And I believe around the world they've actually got more of tracking stations than even NASA does. I think they've got 4 at the moment, and they're looking at expanding even more. Now, Aidan, last month's speaker who talked to us via Zoom, actually mentioned this particular site, which is just north of Perth. Down the middle bottom there is reports actually from the Proceedings of the Royal Society that scientists have managed to detect supposed damaged haemoglobin from a T-Rex dinosaur, and they did that via a new technique using Raman spectroscopy. And I believe even our speaker tonight may know something about Raman spectroscopy, and if you ask her very nicely, she might tell you as we're going through. I think it's still contentious because extraordinary claims require extraordinary proof, but the technique that they used was pretty convincing. And the last one over in the bottom right-hand side of the screen, NASA has a satellite that is unfortunately coming down to Earth too quickly, the Swift Observatory, which is a gamma-ray observatory, and they've recently issued the contract. So in other words, they managed to find some money to try an experimental mission to send a craft up to it to try and boost it back up to a higher orbit. Now this particular spacecraft, this observatory has never been designed to be boosted or moved around or reoriented, so it's going to be an interesting test. And of course, if you're able to send a vehicle up there and interfere with satellites, then obviously you would think there's security concerns between countries with doing that as well. So they'll have to play that fairly carefully, I would think. Okay, so welcome if there are any new members to the Society. The new members that we have today are Caro and Juna Holweg, Fabiola Cerruti, Rosie and Hannah Kirsty, and Ben Skipper, Chris Ansell, and Angela Goyle. Are there any of them here tonight? Hey! You're Caro from memory, aren't you? Yeah, I met you at the public night the other night. Welcome to the Society. Our secretary will now put her hand in the air so you know who to say hello to if you haven't actually met her yet. All right, so this evening I'll go quickly through the events of the past and the coming months. Then the Nobel Prizes were mentioned recently, and indeed one of my old lecturers from chemistry at Melbourne University received the Nobel Prize in chemistry. He was one of the three that was got, but I won't show you the Nobel Prizes. I'll show you the opposite ones, the IgNobel Prizes, as we do this time of year, and they're usually fairly funny, some of the real research that is actually done. Then I'll throw over to Chris for the Astromofo, the photo challenge, and then Guido for Sky for the month. And then Jennifer, I'll then ask Jennifer to come up. We might break for a tea break before then, just to make sure everything is all okay, and then come back in for the main talk. Then if we have time, and if we don't have time, it'll go up on YouTube afterwards, but we'll look at what happened to the Mars helicopter, the Ingenuity helicopter, that no longer up there working. All right, so recent events for the Society since we last met. We had the TLD, the Telescope Learning Day here at the Briars. We had 66 in attendance, but as typical for a Telescope Learning Day, it was a complete cloud cover, so we couldn't actually see the sky. But they at least had talks during the day beforehand and help assembling their bits and pieces into working telescopes. Then we had the committee meeting, and a lot of that was going through the calendars next year. So there are two calendars. One is the calendar of events, which is still being drafted. And there's also the pictorial calendar, which is the sort of the one that you buy for Christmas with all the pretty pictures that MPAS members have had in your calendar. And that is coming pretty close to being ready to be printed. Public night at the Briars is a few days later. We had 80 here and no clouds, so that went really well. They heard Trevor talk there about interstellar visitors to the comets from outside the solar system. A week later we had Tim Patson here, gave the first of the Indigenous astronomy public nights, and that was sort of covering the constellations that were visible at this time of the year in the sky. Then the Cosmology Discovery Group was here on the Saturday as well, and there's a couple of talks there that were cosmology related. And just a reminder there that Brian Cox has announced during the month that he's coming back out to Melbourne for a couple of days. And those that are interested in coming as part of a group from the Society, we've already got 5 or 6, I think, put their hand up. Just approach me if you like. Now, coming up, there's a picture of what the calendar is probably going to look like at the top there, if you're thinking of things to add to your Christmas stocking wish list to buy. That hopefully will be there in a couple of weeks' time. Tomorrow night we've got Yarra Valley Grammar here at the Briars, so they'll be next door at the camp, so we'll be starting at 7:30. We're expecting about 65 year 3s. Catherine and I will give that talk. Committee meeting is the following Tuesday. Then at this stage, the Scouts, Cubs and Guys night, we don't have any bookings, so it's possible that 1 or 2 days beforehand we may call that night off, as usually is the case if we don't have enough bookings. Next public stargazing night, we've got Trevor speaking again, and we've got 92 at this stage booked for that. On the 14th of November, we've got a second Indigenous Astronomy night here at the Briars with Tim, and there is still plenty of room at that one for booking. Then the next night, on the Saturday night, we've got the Freemasons turning up here for a stargazing night. I think it's our first Freemasons night that I certainly recall over the years, and Chris has arranged that. And I think this is a Greek flavour of the Freemasons. So I don't speak Greek, so Chris will be talking at that one.
Get the truth about the moon landings from
Ah. And then the next meeting here is on the 19th of November. The next Cosmology Discovery Group on the Saturday is on the 29th of November. And we've got the Christmas concert coming up on the 6th of December, where we've already got some bookings for that. All right, now for the next 5 or 10 minutes, I'll show you a highlight of some of the Ig Nobel Prizes. So each year they honour scientific achievements that first make people laugh and then make them think, and are usually presented by real Nobel laureates who have won the real Nobel Prize for their work. The prize money is $10 trillion each, and that 10 trillion is in Zimbabwe dollars. So it's, I don't know, probably worth $1.50 or something like that, but they each get given a $10 trillion genuine note of currency. And they only get a couple of minutes to present their work, otherwise someone comes up and starts telling them that they're bored. And usually it's a little girl who's about 7 or 8 years old, but she couldn't make it tonight, so they had to give it to someone else to stand in to do that role, to keep them under control time-wise.
Tonight, we honor some remarkable individuals and groups. Every Ig Nobel Prize winner has done something that first makes people laugh and then makes them think. The Ig Nobel Prize ceremony is produced by the magazine, The Annals of Improbable Research, and produced in collaboration with the Boston University College of Communications. And special thanks to everyone here in the audience who bought an Ig Glorious ticket, which helps support this. Now it's time for the grand entrance of the new Ig Nobel Prize winners. The winner is from the USA. The Ig Nobel Literature Prize is awarded to the late Dr. William B. Bean for persistently recording and analyzing the rate of growth of one of his fingernails over a period of 35 years. Please welcome Dr. Bean's son, Bennett Bean, who will accept the prize on behalf of his father.
Thank you all. As you can see, I have done nothing to receive this prize. My father, however, did a great deal to receive this prize. For years, he measured the length of his fingernails. He also would use the family to check. So we all had our fingernails done. And he would file a little mark and then watch carefully as they grew. I am one of 2 survivors of his patient pool, because one of the wonderful things about doing a long-term experiment on yourself is you never lose anybody to do it on. As long as you're alive, you have a subject, and there are no legal complications either. It's simple. You're there, your fingernails are there, and you can continue endlessly to measure them. So I would like to thank you all very much for the honor. Now, in the case of the honor, it seems to me that the committee waited a little too long because my father died before he could receive it. But then you're never sure about what you're going to be remembered for after you're dead.
The Ig Nobel Psychology Prize is awarded to Marcin Zajankowski and Gilles Gignac for investigating what happens when you tell narcissists or anyone else that they are intelligent.
Okay, Gilles, so this is how the Ig Nobel audience looks like.
It does look like a random sample, but also a lot of randoms.
Hold on. I think that this side is very intelligent.
This side, Marcin, not so intelligent on this side.
Okay, let's measure their narcissism. My smart side, on a scale from 1 to 5, how narcissistic do you feel right now? I get the mean of 3.98.
Okay, now this not-so-smart side, what's the narcissism level, 1 to 5? Give me some numbers. We'll get some numbers. Okay, Marcin, it's coming out to 3.71.
Okay, let's do some stats. It's P equals 0.04.
And that is statistically significant.
See, I told you that telling people they are smart increases their narcissism.
In conclusion, if you're special and you know it, clap your hands. If you're special and you know it, clap your hands. If you're special and you know it, and you really want to show it, if you're special and you know it, clap your hands.
And the Ig Nobel Biology Prize is awarded to Tomoki Kojima, Kazuto Oishi, Yasushi Matsubara, Yuki Uchiyama, Yoshihiko Fukushima, Naoto Aoki, Sei Sato, Tatsuaki Masuda, Junichi Ueda, Hiroyuki Hiroka, and Katsutoshi Kino for their experiments to learn whether cows painted with zebra-like striping can avoid being bitten by flies.
Ladies and gentlemen, we are deeply honored to receive this award, and we are grateful to our colleagues, friends, and families. And we would like to extend our heartfelt gratitude to the organizers and the esteemed panel of judges. These awards serves as a motivation for us to continue striving for excellence and contribute positively to our our irritating me. Excuse me. Okay, we demonstrated that, stripes discourage biting flies from landing using cow painted zebra-like stripes like this. Thank you very much.
The Ig Nobel Chemistry Prize is awarded to Rotem Naftalovich, Daniel Naftalovich, and Frank Greenway for experiments to test whether eating Teflon, a form of plastic more formally called polytetrafluoroethylene, is a good way to increase food volume and hence satiety without increasing calorie content. The winners could not travel to the ceremony. Their acceptance speech will be read on their behalf by Nobel laureate Mungi Bawendi.
This is the acceptance speech for the 2025 Ig Nobel Chemistry Prize. It was written by co-winner Rotem Naftalovich. I am delivering this speech on his behalf. Esteemed colleagues, confused relatives, and curious bystanders, thank you. I am deeply honored to receive the Ig Nobel Prize for research that makes people laugh, that makes them think, and occasionally makes them question my judgment. Science is a journey paved with strange questions and sometimes stranger answers. May we never run out of either. Thank you.
The Ig Nobel Physics Prize is awarded to Giacomo Bartolucci, Daniel Maria Busiello, Matteo Ciarci, Alberto Cotticelli, Ivan de Terlizzi, Fabrizio Almeida, David Ravignas, and Vincenzo Maria Cimenti for discoveries about the physics of pasta sauce, especially the phase transition that can lead to clumping, which can be a cause of unpleasantness.
We know you all might think that this work confirms all the stereotypes about Italians, like that we only think about food. But this is not true. In this work, we studied the phase behavior of protein mixtures. But first, let me say a few words. Ciao mamma. Ciao Anna. Ciao va. Ciao papà. Ciao. A perfect ketchup paper is characterized by a silky and creamy sauce that makes this dish delicious and iconic. However, achieving that perfect sauce is challenging. At high temperatures, cheese proteins aggregate, form clumps, and end up in a big, giant, unpleasant clump, the mozzarella phase. I think we discovered the only case in which Italian mozzarella is a bad thing. However, there's a way to avoid it, adding starch to the sauce.
No starch.
Studying protein aggregates is believed to be very important in several fields. Origin of life, the formation of amyloid fibers in Alzheimer. Today is also very important to create a perfect ketchup paper.
Sta in fronte a te. Sta in fronte a te. Forza roba lì!
So that was the Ig Nobel Prizes. The striped cow, incidentally, the stripes reduced by 50% the annoyance of the flies and the biting of the flies. So just remember that when summer comes along, and notice that pattern there. Make sure you wear that during the summer, and it'll keep the flies away. An interesting one in the past that Karl Kruszyniewski, that most people in Australia will recognise from the media, he also many years ago received the Ig Nobel Prize because he did an Australia-wide survey on the colour of belly button lint, and came to actually find that it was a particular blue colour. As a result, Australia-wide, of thousands and thousands of responses, we collated them all. And with that, I'll throw over to Chris.
Welcome to AstroMofo number 27, Comets and Asteroids. So for the uninitiated, AstroMofo is the, hang on a second, monthly photo challenge, where members are tasked with photographing particular objects or a particular topic, and the last one was comets and asteroids, so minor bodies in our solar system. And the first image I've got here is taken by Guido Tack, and if you like this one, you better buy the calendar because it's in the upcoming calendar as well. So Guido took this one here at the Briars on the 26th of the 9th with a 420mm William Optics telescope, and I also was with him at the time but didn't have as much success. So that's our first image. So the challenge, this one was completed by Guido Tack, Michelle Sykes, Greg Walton, Sylvie Grandit, me, Chris Kostokanellis, and Fred Prater. Had a very late submission by Fred, but well worth it when you see it. And this one here was by Michelle, taken from a van-mounted Seastar S50 in Rosebud. I don't think it was van-mounted like the tracking system we saw in the talk the other month, but probably similar setup. And Seastar image there, so quite nice. And the next one is by Sylvie with a Seastar as well. So about 13 minutes worth of exposure there. So the comet that we're looking at, C2025 R2 Swan, is an open or very long period comet, and that's where it gets the C from in its name. 2025 is the year of its discovery, and R2 is the month and the number of comet or object that was discovered in that month. So it was discovered on the 11th of September, hence the R, and the 2 means it was the second object of its type discovered in that time frame. So it's thought to go around the sun about once every 650 years or so, plus or minus 70, so around about 654-year period orbit, so fairly long duration, not expected to be seen by anyone in this room again, I suppose. And the SWAN was the instrument that imaged it, that first saw it, and the SWAN instrument is on the Solar and Heliospheric Observatory, which is operated by ESA and is orbiting at the L1 Lagrange point. And that instrument has discovered around about 5,000 comets so far. Okay, a couple of images by Greg here, and with the top one there, they're pretty short exposure images, so not as bright as the other ones. They're only 3 seconds with a 135mm lens on a Pentax camera, and you can see Mars in the bottom of that photo as well, and the other one is with a 400mm lens. So similar sort of focal length to Guido's shot, but obviously a very fast exposure because it's not tracked, so hence it's not as bright, but still appearing there in the image, and imaged from Bond Beach. So Swan actually came to perihelion, which is the closest approach to the sun, on the 12th of September, and that was only 1 day after it was discovered. So very, very close to its discovery days when it was closest to the sun, and it was only around about half an astronomical unit from the sun at its closest approach. Its closest approach to Earth is coming up on the 20th of October, so there's a chance that it might brighten up, and it's also a bit higher in the sky as well to be able to see too. So keep an eye out over the next few days on the western sky, and Guido I think will go into a bit more detail when he does Sky for the Month about it. This is my capture of it, pretty much at the same time as Guido, but I didn't have much luck. I had there was a lot of cloud, and I didn't get too many shots. So that's the best that I was able to manage. And this one was with a Nikon lens on my Astro camera. So 70 to 200 millimeters at 200 millimeter focal length. And the other one I'll show you is earlier this month, sorry, in August, I posted an image that I had taken which had a little asteroid on it, and that's the image on the right, 24th of August, and the asteroid there was Athamantus. So that's, the object there is NGC 6604 is the nebula, and the image on the right there is the one from August, and then I imaged the same area last night, and you can see that the circled dot is not in the other photos. So that was the asteroid Athamantus, and between then and yesterday it had moved on. I did actually track it down and managed to capture it it's still in Serpens, but it's moved on. It's sort of between, Scutum. It was in Scutum, not Serpens, and now it's sort of between Skilton and Capricorn. And what this is showing you is there is anyone who uses Siril for image processing. Siril also does astrometry, so it'll look at your image and it'll tell you which part of the sky you're looking at, and then it'll also identify objects in your image. So you can click on different types of objects that you want to see. It'll show you stars, nebulas, and there is also a setting where it'll show you solar system objects. So I clicked on that, and it did show up 3 other solar system objects which are in that field of view. Right in the middle of the image there is our target. Where's my pointer? Right in the image, right in the middle there, sorry, is our target, Athamantus, which is where it's moved on to. And then over here, it's also telling me there are 2 other objects in the image as well. So Athamantus, what is it? It's got a mean diameter of around about 118 kilometers. So that's about the size of it. And it is around about 1.89 times 10 to the 18 kilograms in mass. So it's a pretty heavy, well, you know, you want to lift it, but it is not a huge asteroid. It's 118 kilometers, but not anything small either. And it is a main asteroid belt object as well. We're stuck. Here we go. Another one that I imaged last night as well was Ceres, the minor planet in the asteroid belt, and again identified it the same process in Siril using the astrometry and the annotation function, which picks up other objects in the image as well. And Ceres is up right near the top. You can see the two bright stars. Ceres is the one on the top. And this was imaged with 200 million Newtonian in my Astro camera. So Ceres was originally announced as a planet when it was first discovered, and that was by Giuseppe Piazzi in 1801 at the Palermo Observatory in Sicily. It was then classified as an asteroid, and then later reclassified as a minor planet. So it is orbiting between Mars and Jupiter in the main asteroid belt, and it has a diameter of around about 940 kilometers. It is a minor planet because it's spherical. Asteroids don't have enough mass to make them spherical, so they're not quite planet status or minor planet status. And its orbital period is around about 4.6 years. A couple of images by Fred Prater, which was sent to me today as well. So this is with just a standard lens, and Fred says he's got a few images, so I'll just read out what he says about them. Here are my photos. One is just a regular camera shot, part of a movie, which is this one here. So he's done a bit of a time lapse on it, which I don't have. But it's basically what you can see with binoculars or your eyes if it's really dark and you can still focus. Another is an analysis I did to estimate the intensity change of the coma. It's very rough and probably includes local sky changes. Not enough time to do a proper job, but it shows what science might be possible from your backyard. So the next images are Fred's other images over the course of time. So the first one, 28th of the 9th on the top left, 7th of October on the top right, and then the bottom one there is from the 9th of October, and the one on the bottom left is 10th of October. and there's one more as well. So he's been imaging it whenever he can and just comparing the brightness of the coma as it's progressing around the sun, or away from the sun. We've got a final image there from the 14th of October, so that was just from last night. So it does seem to be dimming, and Fred's plotted it out on a star chart there to show when his images were taken, at what position the comet was in the sky as it's going across. So thanks very much, Fred, for those. Okay, so that's our scoreboard at the moment. We've got one more challenge to go. And the top three, they're pretty tight. So me, Greg and Sylvie leading the way over there. Good job, Sylvie. So there's also, you've got another chance this month to get your name on that leaderboard. And our target is globular clusters. So there's a couple in the sky at the moment. We've got 47 Tucana, which is the obvious one. If you are early enough to get Omega Centauri in the southwest before it sets, you can get that one too. M2 in Aquarius, M30 in Capricorn, and M4 is near Antares as well, which is a nice one, but that's setting earlier and earlier. And also NGC 6723 in Corona Australis, which is a globular cluster near a bit of a reflection nebula there, and a dark nebula, which is a pretty nice image to capture too. Our Hubble challenge also continues, so we'll keep going with that. If you've got images from the month to compare to Hubble images, and the current Hubble images from the website, a few globular clusters there, M2, 47 Tucana and M30, as well as a couple of planetaries in the Sombrero Galaxy. And also, when the month ticks over to November, they'll put up some new images, some new objects on their website that you can target as well. So just remember to give a bit of information when you send in the photos about what you're actually imaging and how you've imaged it. And also, if you are doing a Hubble comparison, give me the image that you're comparing your image to from the Hubble website or from the Hubble library. And that's me. Thank you very much. Any questions, anyone? Too easy.
All right, welcome to Sky for the Month for the rest of October and the first half of November. Unfortunately, that first image didn't come through, so let's just quickly go to the next one. So here's a look at the solar system from the top for the next month. So you can see here with the sun in the middle, this is basically tonight. Let's zoom in a little bit to the inner solar system. We're zooming out first. Okay, so we have Saturn and Neptune here, still pretty much in the night sky for the entire night. And Jupiter is coming, we are coming closer to Jupiter now as well, so it will rise a bit earlier compared to last month. So we should be able to see it again during our summer public nights as well. So this is the inner solar system, so we can see what it's going to look like over the next month or so. As you can see, Venus is disappearing from us, while Mercury is now moving towards its greatest elongation, so where it's basically at a 90-degree angle between the sun and us. So that's a good time to observe Mercury, as we'll see in the overview in the next few slides as well. All right, and you can see the interstellar comet 3I Atlas here making its way through the solar system as well. So Mars is down here, so it's currently basically behind the sun from us almost already, so not observable. But as you can see, 3I Atlas, the interstellar comet, made a very close approach to Mars earlier, and it's going to reappear from behind the sun towards the end of November. So we hopefully get a chance to see it from maybe early December or so. All right, so that's the Briars at around 7 p.m. on the 1st of November. So let's have a look at the early evening sky there. So the sunset now is going towards 8 p.m. or so. And we will have the new moon on the 21st of October, and then the full moon on the 5th of November, and another new moon on the 20th of November. And so this is now at 10 to 9 p.m. roughly, and you can see some of the planets still in the sky. So we can see Mars and Mercury still very low to the horizon here. I think Mars setting around 7 p.m. isn't quite right here, so this is already almost 9 p.m., but it'll be very, very close to the horizon. And yeah, Mercury will be at its greatest elongation on the 30th of October. So that's when it's basically the furthest away from the sun as seen from the Earth. So that will be a good opportunity to observe it. And Mars is actually now getting really close to Mercury at the moment. So it might be, like if you have a very clear western horizon, it might be an interesting thing to observe those two planets very close together towards the end of the month. I think the 19th of October is one opportunity, but then there's another one a couple of days later or so, a couple of weeks later. The other planets we can see here are Neptune and Saturn in the middle there. So both of them are now past opposition, which means that they rise pretty early now. They are pretty high up in the sky already at sunset. So really nice observing targets and basically available all night at the moment, so especially Saturn. And I think that's all on this slide. So let's move about an hour or so further into the night and have a look at the stars and constellations. So this is now around 10 p.m. and we can see the main stars in the sky. Let me see if I can get a laser pointer here. So we have Fomalhaut basically at the zenith, so straight up from us. So that'll be one of the bright stars you can definitely see. And then the other ones that are going to be prominent are Acana here in the towards the southeast from the zenith. And then a lot of the other bright stars are kind of close to the horizon. So we have Antares almost at the southwestern horizon. We have Altair also getting close to the northwestern horizon. Canopus in the southeast, and the Southern Cross down here with the two pointers also pretty low on the horizon now, around 10 p.m. And you can already see Rigel in Orion now rising at around 10 p.m. as well on the 1st of November. So just looking at the constellations, Scorpius now is basically very close to the horizon as well, and yeah, Orion will be rising around 10:30 or so. So that definitely now marks the transition from autumn into from spring into summer over the next few months. All right. Well, this is going a bit too quick, but if we just now move forward for the next couple of hours in the night, where we can see Saturn and Neptune there basically during the entire night. Uranus here is rising around 10 p.m., Jupiter around 2 a.m., but it's getting earlier and earlier every week after that, so we will get it back into the evening sky over the next few months as well. And then sunrise now is around 6:15, and you can see Venus there very, very close to the sun, so not observable for the next month or so. All right. The apparent sizes of the planets, not that interesting at the moment because most of them are not really visible. So we have Saturn here, and that's the main one. And the rings are basically closed now again. So they opened up a little bit over the last few months, and we're now closing again to about 1 degree. So you can only see them through a telescope as basically a line through the planet, almost edge on. And yeah, all of the other planets, Jupiter appears very large here because we are actually moving closer to it in its orbit. So it'll basically appear larger and larger over the next few months when we are getting closer. Comets, and only listing the ones that are brighter than 10th magnitude. I've only got C2025 R2 Swan that Chris already talked about here, closest to Earth on the, I think, 19th or 20th of October. I think you might be right that it's actually the 20th of October. And around magnitude 6 to 7. So definitely nicely visible in binoculars or with a small telescope. And this is basically the position today. So that this is the western horizon with Antares there. And I think this should now move forward one day at a time, basically. Every step is 1 day. So you can see it rise higher and higher in the sky over the next 2 weeks or so. So still a very, very good opportunity to observe and photograph it. Meteor showers, there's a couple of them coming up over the next month. We have the Southern Taurids between the 10th of September and the 20th of November, basically just past the peak, but that was around the full moon. The Orionids between the 2nd of October and 7th of November, peaking on the 21st of October, so not too far from now. And they're usually also visible like 2 or 3 days either side of that peak. Or the peak is pretty broad. And this is at least this time around the new moon, so not really impacted by moonlight. And the best time to see the meteors is just before sunrise, also from around 4 a.m. or so, because we're basically moving through this debris field in our orbit, which means that when the Earth basically rotates into that debris field, that's our morning hours, right? So the meteor showers are always the most visible during the morning, early morning hours. And then we also have the Leonids from the 6th to the 30th of November, peaking on the 18th, so that's more for the end of next month. And I think that's all I had for tonight. So sources, as always, Stellarium, NASA Eyes on the Solar System, and the Astronomy Yearbook. Phil?
You said the Saturn's rings are now becoming edge-on again, is that right?
Yes. So
they were like a few months ago, weren't they?
Yeah, exactly. So the rings were completely closed, so really completely edge-on in, I can't remember, February or March. But at that time, Saturn wasn't really visible, so it was very difficult to observe it. And then they open up again a little bit and now close up again, but not fully, only until about 1 degree or so, and then they will open up again.
Is that because of where it is?
Yeah, it's about where it is and where we are in the relative orbits, and how the orbital planes kind of align with each other. And so this is now a really good opportunity to actually see the rings basically closed, right? Because it's in the sky for the entire night. Yeah. Any other questions?
All right, I'd like to introduce our speaker tonight, Jennifer Quinlan, who's doing her first-year PhD at Monash University. She has a background, she's got a Bachelor of Science honours, I think, in, there was maths and astrophysics and a bit of biochem in there as well, from memory. And she does own a Dobsonian, so she's not just a theoretical physicist, so she does actually get out under the sky as well. She'll undoubtedly talk about the rover as well as part of her experiences. And I'd also ask you to hold off any questions if you can until later in the talk, and then I'll run this microphone round and get your questions. Otherwise, we won't. The people who watch this later on YouTube won't actually be able to hear the questions if we do it as we go along. All right. Well, with that, we're going to learn all about cosmic fireworks, the explosive fates of massive stars, and thank Jennifer for coming along tonight.
Awesome, thank you so much, Peter, for that intro. So today I'm going to talk about supernova, which are basically big explosions when massive stars die. So I thought that would be a good title, Cosmic Fireworks, the Explosive Fates of Massive Stars. So to start off, this is an image of supernova 1987A. This is a near-infrared image, so it doesn't look like this if you looked at it from a visible wavelength, but this was taken by JWST, and this is a remnant from a Type 2 core collapse supernova, and the core collapse supernova is what we're going to discuss in more detail today. But first, we'll strip it all down. We'll talk about, well, what are supernovae? how do they happen, what types of stars experience this, and if a star doesn't experience this when they die, what does actually happen to them. We'll also talk about these explosions and why they're so important for our universe, and in particular, how do they actually contribute to life as we know it. And we'll also later discuss, as Peter said, a little bit about my time when I worked on Monash Nova Rover and how we tried to detect life that isn't on Earth. So first, we'll begin with our sun. So our sun, in comparison to Earth, is extremely big. If we tried to fit Earth into the sun, it would fit we'd be able to fit 1 million Earths into it. So it's really big, but compared to stars within the universe, it's actually relatively small. There's stars in the universe that are up to 100 times the mass of our sun. But stars that are roughly the same size as our sun, we refer to as sun-like stars. And you can see in this diagram, they have a fairly boring fate. Like all stars, they kind of begin in these dense clouds of dust and gas, star-forming nebula, and they get formed. And for a sun-like star, they're usually between 1 to 8 solar masses. And then what will happen to a star of that size is they will start burning hydrogen as a main sequence star, which is where they'll spend most of their life. And that's currently what our sun is part of, like that's what its phase is. It's burning hydrogen in its core. But eventually that will run out. And for those low average mass stars like our sun, they'll become a red giant. And eventually that will collapse and it will shed its outer layers, and that's what we see as a planetary nebula. And its core will collapse into a stable white dwarf. However, for massive stars, after they come off the main sequence, so when they stop burning hydrogen in their cores, they become red supergiants. And they will eventually collapse too, but when they do so, they'll release a heap of energy in a violent core collapse supernova explosion, which you can see down the bottom right there. And they'll either leave behind a remnant of a neutron star or a black hole. So I'm going to dive into a bit more about what happens on that massive star side. It might get a little bit physicsy, but I will explain it in a bit of a simple format afterwards as well. But basically, hydrogen is the most simple element in the universe, and it's the most abundant element we see in stars. We can see in this image on the left here, stars are made up of multiple layers, and what we're going to talk about now, it happens in the innermost layer of the core. So basically for a main sequence star, and we're going to talk about the massive star, which is 8 solar masses and above, inside the core there's lots of hydrogen and it's extremely hot. So when we heat things up, they gain lots and lots of energy, and in a main sequence star's core, this triggers the burning of hydrogen, which we also know it as nuclear fusion. And this reaction is what's happening in the top right. We can see that hydrogen in the core exists as these isotopes, a deuterium isotope and a tritium isotope. And these isotopes, when they're really hot, will fuse together in fusion and will create a helium-3 particle or an alpha particle. And in that process, importantly, will release lots and lots of energy. So just put that simply, basically 2 protons, simple protons, heat up, fuse together, create a helium atom and produce lots of energy. But like all fuel, eventually it will run out, and for stars, eventually they will fuse all of their hydrogen to helium in their core. And this is when a helium core will form, and what will happen is the outer shells of that star will start to burn hydrogen. And when this happens, it starts to expand, and that's when it becomes, for a massive star, a red supergiant. So pretty much once this happens, you've got a helium core. This will begin to fuse again, but instead of fusing to things like helium, it's going to fuse to heavier elements, because now you've got 2 heavier elements fusing together to form an even heavier element. And this is really important because now we're synthesizing things like iron, carbon, really heavy elements. And as mentioned before, these stars have really big masses. So what happens when we run out of fusion, the big mass, gravity will pull in. But usually when it's on the main sequence and we have fusion, which releases a lot of energy, it will push out against that gravitational pull inside. So usually it's nice and balanced, and this is called hydrostatic equilibrium, and that's what happens on the main sequence. But once it runs out of hydrogen and this fusion isn't happening anymore in the core, all of a sudden gravity is going to take over. So what happens when fusion stops? Well, basically for a massive star, it's that. So we get a star collapsing in on itself because gravity will take over, and now there's nothing inside that's counteracting that pull inwards. So now it all comes in, and what will happen for a massive star, a shock wave will propagate out, basically expelling all of those outer layers in a violent explosion. So the aim of my research is pretty much to try and understand the physics happening on a deeper level in these stars that drives these massive stars to explode. And I do that using computer simulations to basically simulate these models and understand, well, what physical parameters cause stars like this to explode. So these are some of my models that I've made so far. Basically, these explosions happen so quickly that we simulate our models on timescales of milliseconds. So a lot of these models have only run to half a second after they've exploded, but that's so we can break down what's happening. Here I show some of the models I've simulated at different times right after their initial explosion. So these are like 2D snapshots of a 3D explosion, and all these are looking like I'm standing on the equator of the explosion. So that's kind of like the viewing angle we're looking at. You can also see these magenta lines outlining a lot of the explosion. That's actually the shock wave I was talking about that happens when the star collapses in and propagates outwards. And what we do in our models is we track this shock wave propagation over time and see how big it gets. In the middle of my models, you can also see those kind of dark circles. That's actually a protoneutron star forming as well. So that's that remnant neutron star that will form as a result of these core collapse supernovas. So yeah, and if you want me to dive a little bit more, these are for 3 different solar mass progenitors. So to break that down, a progenitor is the starting star before it explodes. So at the top left, I've got an 8 solar mass progenitor. So it started as an 8 solar mass star and then it exploded. The top right is a 13 solar mass star and the bottom's a 20 solar mass star. Now, the most exciting thing about these explosions is that every single element we know was created by ancient stars exploding in a supernova. So the saying that we are made of stardust is actually quite literally true. Like, we've all made up of those elements that have exploded from ancient stars. So when I analyse my supernova models, we try and look for artefacts like jets and outflows of matter. So if you have a look at that top right model, you can see this big jet on the left pushing outwards. And basically that's a big jet of matter that's been expelled during the explosion, and that's got elements like carbon, iron, nickel being pushed out into space. And we can analyse those jets and see what kind of elements have been synthesised within that ejected matter. Now, going a little bit into these elements, these supernova explosions, although they're the death of massive stars, they become the birthing ground for the formation of new stellar objects and even life. So when they leave behind these remnants like black holes and neutron stars, they also eject all these elements into space, which are synthesized during that nuclear fusion stage. And these elements consist of like carbon, oxygen, nitrogen, iron, and these are all necessary for molecules and elements that we see in life as we know it. So these elements are synthesized, released into space during supernova. They become the building blocks of life, and you can see here I've got things like water that's made of hydrogen, oxygen. You've got trees that expel carbon dioxide. They take in carbon dioxide, expel oxygen. We've got macronutrients like carbohydrates, proteins, and lipids or fats, and also nucleic acids. They all contain elements from these explosions and are necessary for the building blocks of life. So let's look at like life beyond Earth. So how can we look for evidence of life on other planets? So firstly, we can detect, like, let's look at exoplanets. So exoplanets are like planets that are outside our solar system. We can actually detect if an exoplanet could have life on it, which is kind of crazy because you'd think of that 50 years ago, didn't seem possible, but now we can actually analyse their atmospheres. And the way we do that is we first detect an exoplanet's there. So we can do that by looking at the transit method. So we look at a star and we look at its luminosity over time, so how bright it is over time. But if a planet passes between the star and us in front of that star, the light's going to drop a bit. And then this will happen periodically because planets orbit around their host star. And what we tend to see is like that light curve over there, we see that luminosity and then we see the dip and then we see it come back up. And that's how we can detect an exoplanet's there. And now that we have advanced spectrometers and telescopes, we can actually use transmission spectroscopy, which is on the right of that image in the top right, which actually uses a similar method but looks at the light coming through. And the light close to that planet, if you think about our planet, we've got the atmosphere just around us. Light coming from behind that is going to shine through that atmosphere. And what we can use is spectra, and in this case absorbance spectra, where basically that light coming through, elements that are present in that atmosphere are going to absorb some of that light, and they will show up as dark lines on that spectra. So we can see here we've got, like from this example planet, we've got H2O, carbon dioxide, that is all being absorbed in that planet's atmosphere's light, and we can see that just from a spectra, which is pretty cool. On top of that, we can also look at planets within our solar system, especially those that have a surface, like Mars. And the way we do that, which most of you probably know about, is we can send technology like rovers to those kind of planets, and they can do surface exploration. And what these usually have on them are life detection techniques like spectroscopy and different types of spectroscopy, which I'll talk about in the next few slides. They also have very good microscopes to analyse different samples and different parts of the surface. And they also would look for geological signatures like cracks, because if there's cracks forming in the ground, that could be evidence that water was once there. Look for different fossils and other formations that could indicate that life was once there as well. So when I was at uni in my undergraduate years, I actually worked with a student engineering team called Monash Nova Rover. So basically what we did was we made little rovers that were meant to be like Mars rovers. And basically what we did with these rovers is we took them to competitions to compete against other universities. And in those competitions, it had to complete certain tasks. So you can see that it's got different forms. So basically it can fit different payloads. So in the top right, you can see it's actually got a mechanical arm on it. So that mechanical arm is used in tasks like down the bottom where we're doing a field test. That's actually a prototype of kind of like a spaceship kind of thing. And what we have to do is we have to firstly drive it up a ramp. Then that arm will do things like put in a USB into a USB port. It can also press keys on a keyboard. So basically we've got to make it so it can complete all these little tasks. On top of that, we also work on the chassis, which is the wheels and the suspension, and we make sure that that can go over rocky terrain. It can go over steep hills, down and uphill. Also, we make it so it can operate remotely. So we're not allowed to see the rover in competition. We're like in a base station, and basically only cameras on the rover can tell us where it is, how we operate it. So that's how we do all our training. We do it like we're at a base station, and we don't look at where the rover is. Lastly, there is a science payload that we put on it. And the idea of that payload is to complete certain tasks which involve mainly life detection. So we get told to go to different samples out on course, and we basically go to each sample and say if there is life, no life, and if that life is alive or if it's extinct. And we have to basically give the judges our thoughts and we have to also give them evidence as to why we think there's life, no life, whether it's living or whether it's dead. So I worked on the science team, and I worked on those life detection techniques. And on the top left there it's a bit broken down at the moment, but that's basically a rundown of what our science payload looks like. So obviously you can see all our electrical boards on the left, which basically power, they're not all there at the moment, but they power everything that goes on within that payload. But the main thing that we want to do is we want to detect 4 types of molecules, which are like the biomolecules for life. And those molecules include proteins, carbohydrates, lipids, and nucleic acids. In comp, we need to, as I said, identify 4 sites and determine if there's life or no life, and if it's alive or not alive. Then we have to distinguish, okay, well, what do we want to detect, and how does that relate to whether it's alive or not alive? So with us, we decided to add biochemical assays. However, the biochemical assays we added can only tell us if life is present or not present. It doesn't tell us if it's alive or not alive. But it's a good qualitative test to determine whether we can move forward with that sample or whether we move on. So we incorporated 2 biochemical assays. BCA Gold, which is basically a biochemical assay that detects the presence of proteins. And when a protein is present, it forms this BCA copper complex, which turns the solution gold, as you can see in that image. So on the far left, that's a very positive test, and it's got a lot of protein in it because it's quite dark. The middle one's also positive, just not as dark, because it would be like a linear curve, depending on how much protein's in the sample, how dark the sample turns. And the one on the right's a negative control, and that stayed negative, which is good. Basically, we can measure their absorbance at a certain wavelength, which can tell us quantitatively, so it can tell us how much protein is in that particular sample as well. And we also adopted that on our payload, which you can see in that carousel black box up the top. Basically, there's little squares in it. That's what we put all those cuvettes in. And this is all done on board as well. So we're in the base station controlling this. We don't have access to the actual payload. And basically we sit there and click it, and it goes around one at a time. And then it looks at each individual sample, takes a UV vis analysis of it, which basically gives us a spectra of the absorbance. And then we determine how much or whether there is protein in that sample. The other assay we use is ninhydrin, which is very similar, except it looks for amino acids, which are like the building blocks of proteins. But instead it turns it purple. So it's very dark. Both are very dark assays, so we can also visually see whether proteins or amino acids are present. So this here shows you what we kind of get when we complete these tests. So the top left is a spectra of what we get when we measure the absorbance of how much protein is in the sample. And we look at those peaks on the right at particular wavelengths. So for us, the ones that we care about is the one at 570 nanometers and around 370 nanometers. And we measure that peak absorbance, and then we compare it to a standard curve we make in the lab. And basically, if we put that absorbance on a point on that standard curve, we can actually measure how much protein is in that sample, which is a pretty cool thing to do. In competition, that doesn't always go right, but it's good to have that there, and a lot of the time we get a good qualitative answer anyways, whether protein is present or not. But basically, the higher absorbance, the darker it is, the more protein. But yeah, you can see that method set up. You can see that cuvette being lit up by our 570 nanometer laser, which shows that absorbance. And you can see there that that sample's positive. You can see quite a bright fluorescence of the BCA gold, not fluorescence, absorbance of the BCA gold. And then on the far right is how we collect our samples. So on the front of the payload, we've got mini augers, which basically go into the ground to cache subsurface samples. So basically, when we go into competition, there's some samples we want to get from the surface, but there's also some criteria which says we have to get it from below a certain height of the surface. So that's why we have some augers on there. They basically drill in, cache it into a little scoop. Then we add some buffer solution to make it a solution. And then if you see those labeled, that labeled square thing in the middle bottom picture that's labelled 1 and 2, they're pumps. So they pump up that solution from the scoops into that carousel, into pre-prepared solutions, and that's how we get our results in the biochemical assays. So you can imagine a lot can go wrong on the day with these pumps and everything working, but in an ideal world, we get these biochemical assays, we get these readings, and we get a qualitative and a quantitative answer to how much life is in that sample. However, like I said before, that sample, although it might tell us if life is there or if life isn't there, it doesn't tell us if life is there, if it's extinct or extant, because proteins can be present in extant life and extinct life. So for us, we had to think quite a bit, well, what technique will work to distinguish this? And we came across Raman spectrometry. So basically, this allows us to excite a sample and see what molecules are present within the sample. And what we determined, could be easily seen with Raman spec, is things like fossils, certain types of fossils. They give us a very unique spectra that we can see. And things like nucleic acids, like DNA, RNA, that can also be found, and that's only present in extant living life. So it started off very basic. That was like our very first sketch of what the Raman spec would look like. So you can see the laser's set up perpendicular to the actual spec, and then it gets put on a beam splitter, which is aimed at the sample. Then the laser at a certain wavelength, which we determine depending on the molecule we want to detect, shines on the sample, excites the sample, comes back through the lenses, through the diffraction split, which will split it into different wavelengths. Then it will go along the spectrometer part of the spec and go along those mirrors and shine in on a CCD, which will give us a spectra. So that's a lot of physics in there, but basically that was our first sketch. Then we move across to CADing, so we put it on a computer, and that can actually 3D print some of the parts. And we had a pink rover campaign for one of the years, so we turned our whole rover pink. So the 3D printing ended up being on pink filament as well, which is what you see in that bottom right. That was our first prototype, and that was working really well. And then once we do a working test with the Raman spec, we get a spectra that will look like that. And that one on the bottom left is actually kerogen, which is a molecule commonly found in fossils. So that would be evidence for extinct life. So in terms of what we see during comp, so basically we have extant molecules that we decided we want to detect nucleic acids and lipids because they're molecules we only see in living organisms. And then we also decided we wanted to detect kerogen, which is in fossils, and they're only found in extinct life. So we have those two spectras that we need to find, and what we do is we run our Raman spec, and you can see in that video that we get a spectra on our laptop. That was probably one of our first tests, so not very accurate, but it got very, very good at the end. And basically we get a spectra on our computer, and we compare that to known spectra and see if that molecule's present. And to do that, we had to use two lasers at two different wavelengths. So kerogen can only be found at a 532 nanometer wavelength, which is like a green laser. So we had to have a green laser. And then DNA, RNA, and lipids have a distinct spectra at 780 nanometers, which is like a red laser. So we had to have two different lasers to run those tests. But yeah, so I'll bring it all back to what is actually happening in real life. So this was just in competitions. A lot of the times things went wrong, but it was actually really cool because we've figured out that things like Perseverance Mars rover actually use really similar techniques. So they've got something called the SuperCam, which actually has a spec on it which uses Raman, so that's pretty cool, and we were able to do a very similar thing on our rover. On top of that, like, they also use things like near-infrared spectroscopy, which we were trying to integrate into our one as well, which was really cool to see that they were the lead analytical tools. And the main reason why they're the lead analytical tools in rovers is because they're really quick. They don't require incubation times, or they don't require to be at certain temperatures. You just shine it at the sample and you get a result. Whereas biochemical assays not quite as effective for in situ, which is like on the actual surface analysis, because they need incubation, correct temperatures, and certain environmental conditions in order to work. So we need, like, using those spectroscopy techniques is the leading one at the moment. So it's cool to get a Raman spec working on our rover. But basically, that's pretty much everything we did on Nova Rover, and it's pretty cool to see the techniques that we used on a rover like Perseverance. And yeah, that's pretty much it from me. Basically, if you're going to take anything away from today, take it that life is a cycle, which began at the very beginning of the universe, and the elements that make up me and you were most likely formed billions of years ago in a supernova explosion. So yeah, we're made of stardust. Cool.
Thanks, Jennifer. Any questions from anybody? Fred?
Yeah, sorry, I don't know that one. You know, them spectrometers, are them the spectrometers that was put on a rover to go to Neptune to pick up greenhouse gas emissions 3.5 billion miles away?
Oh, I think these ones are built for like looking at samples that were brought up. These were built on the rover to look at samples coming from like Mars, so where like surface samples. I think though Raman spec can be used for looking at that kind of stuff, but I think it's mostly spectrometry in general would observe those ones. Yeah.
What's a nanometer?
A nanometer, good question. A nanometer is, it's basically a unit. So you have a meter, which is 1 meter. A nanometer is 10 to the negative 9 meters, which is basically 0.00090, or yeah, till you get to 1, if that makes sense. So it's very small, very, very small. But we use it for wavelengths because... Pardon? A millionth of a millimeter. That's a really good way to put it, yeah. So very small. Yeah.
Phil?
Great presentation, thank you very much.
Oh, thank you.
Just like to know, have you thought about what sort of power source you're going to use? If it goes to Mars, I assume obviously you're not using nuclear power for your own particular one. And what's with the pink rover, and what colour do you think the rover would be when it actually goes to Mars? Yeah, so at the moment, yes, it's very much not good, like it would not work on Mars. There's like lots of things, including temperature, that's a big thing. So we use just normal batteries, like they would not work on Mars. So yeah, you'd have to, I'm pretty sure Perseverance uses a lot of different fuel sources, but like solar would be a big one as well. But yeah, ours is using batteries at the moment, and we've got a couple batteries just to power certain payloads as well, like the science payload. We've got so much electronics on there that it needs its own battery as well as the main rover battery. So if we were to send it to somewhere like Mars, we'd definitely have to probably think of how to make it more efficient in terms of power. But the pink rover campaign's a good question. We actually, so when I first started, it was orange, and then we decided that it would be good to spark conversations about diversity in STEM. And so we made it pink, and it actually worked. We go to 2 competitions, Australian Rover Challenge and the University Rover Challenge in Utah. And when we took it to the Australian one, everyone was like, why is it pink? Because it stood out. Everyone's is like silver, black, like just boring colours, and then ours is bright pink. And the whole idea was to spark that conversation, like, why can't it be pink, or like things like that. So yeah, that's kind of how it started, and then like it kind of built from there. Yeah.
Thanks for the talk, Jennifer. I have many questions, but I'll try to stick to 2. The first one is about the chemical assays as compared to the spectrometry. What are the benefits of the chemical assays over the spectrometry? I mean, obviously the spectrometry is easier to do in those environments, but what would be the benefits if you could do the chemical analysis?
For us, the reason why we prefer the chemical assays, or why we would in our particular one, is because in our rover, it's really hard to make it stable, and something like SPEC requires a lot of stability because you can imagine how sensitive like those readings are. So in our comp, a lot of the time when we're looking at spectra, it was super noisy, and we had models to try and cancel out the noise that we compared it to average noise and tried to subtract the noise from the actual spectra, but because there's so much noise, it's basically impossible to do that kind of correction. However, in comps, it's really good to do assays because you can kind of bump around and you're not really going to lose much solution because it's all kind of contained and you can account for those bumps. However, on Mars, and if you've got a company like NASA, they're going to be able to build much better Raman specs than what we would. And they've probably got systems involved to keep it nice and stable when it's taking those analyses in situ. So yeah, that's probably the difference between ours and theirs. We'd prefer the chemical assays because of we're doing it on Earth pretty much, and we've got quite a noisy spec, whereas on Mars, the chemical assays take time and they're quite dependent on temperature, whereas their specs would be a lot more stable and less sensitive than ours. Yeah.
The second question is in relation to the supernovas.
Mm-hmm.
So when you have a core collapse supernova,
yeah.
My understanding was that what causes the Big Bang, the explosion, is that fusion stops and the stuff of the star starts coming in,
mm-hmm.
hits the core, recoils,
yeah.
and that's what we see as the bang.
Yes. Yeah.
So and that you said happens within milliseconds.
Yeah, very, very quickly, yeah.
So the material starts falling in at
mm-hmm.
a really fast, must be really fast speed once the core stops fusion. So the core would stop fusion very suddenly?
I think it definitely would happen over time because obviously it's got to work through those elements. Obviously the outer shells still will burn that hydrogen, so they'll still provide some kind of outwards pressure to stop that gravitational fall. But yeah, once that gravitational fall starts overpowering quite significantly, that contraction and then the bang happens quite quickly. And then we look at that just post that Big Bang, and that what happens between that and then 500 milliseconds after, a lot of physics happens there. So that's why we try and do it on a really small time scale as well. Yeah.
And then what results in either a neutron star or a black hole is the result of that implosion.
Yeah, it's
not so much the core just collapsing, it's everything else falling into it that makes it collapse.
Pretty much. It's actually a big research area because it's obviously a core collapse supernova that will either leave a neutron star or a black hole remnant, but deciding which one actually happens is actually still a big research area. We think it's got a lot to do with mass of the progenitor to begin with, so obviously the amount of mass falling inwards at that ending point, but yeah, that's still a big research area, seeing which one gets formed, yeah.
And I've also heard that there are certain stars that are so massive that when they do collapse, they collapse straight into a black hole and there's no explosion.
Mm-hmm. Yeah.
So is that something that would be part of your research as well?
At the moment, I'm dealing with hypernova models, so we actually really want to see really energetic explosions, so not in my particular research right now. But yes, there's definitely supernovas that don't explode, and that can be a case of one of them, yeah. So hopefully down the track, because I'll look at different types of supernovas after I finish this project, I get to deal with ones like that because they're pretty interesting, yeah.
So the computer simulations that you do, they're obviously not on your laptop.
No.
What do you use?
I'm mostly using Gardi, which is a supercomputer in Canberra. And we also, we use 3D data, which takes up a lot of space. So we tend to run out of time on the supercomputers, so we jump to a couple. So we've used Cetonics, which is Pawsey WA's supercomputer. We used a bit of Ozstar's supercomputer, which is Swinburne's. So yeah, we run those simulations on the supercomputer. And then to get those plots that I showed, I have my own Python code influenced by lots of other great researchers as well. That I basically run that data that's formed from that really hefty code on the supercomputer, get that output files, and I put that through some Python analysis, and that's how I get plots for those simulations, yeah.
So there's no hope of doing it as like a citizen science project and distributing the...
yeah, no. Yeah, not quite, no. Yeah.
Any other questions?
You were saying that these things are happening in microseconds, but the distances involved where travel has to occur would surely exceed the speed of light.
The scale at which we're looking at those simulations was really small. But if you saw the way they're propagating very quick. They're definitely not exceeding the speed of light. But yeah, they're quite close. They'll be traveling at a fraction of that, but they're very quick. But they're definitely not exceeding, because otherwise we'd see every explosion that happens. But yeah, like when we see one, it's happening from like years and years ago when we eventually see some, and that's why it takes like a lot of time to see observations of them. But yeah, no, they definitely don't go beyond the speed of light. Yeah.
Right.
Yeah.
Thank you.
Any others? Okay. One last call. Ben.
Chris asked the question I was going to ask about neutron stars and stuff, but I was just curious, when a star collapses into a neutron star, what happens then? Does it stay as a neutron star forever, or do they fizzle out eventually, or do they then explode?
Yeah, that's a really good question. It kind of depends on what's nearby. Sometimes they can go into binaries depending on what's nearby, and that can be really interesting. And if you've heard about gravitational waves, sometimes because they're very dense objects, they can influence gravitational waves too, especially if they're in binaries. But yeah, once they're in that kind of form, they're pretty stable. But what we're looking at, we look at highly rotating magnetized progenitors, like stars to begin with. And a lot of the time they can actually form pulsars, which are a type of neutron star, but they emit pulses because they're magnetized. So like lots of, depending on where they are, they can become many exciting things.
If you have binary neutron stars and they crash do they ever crash into each other, or do they sort of...
Good question. Depends on what type of masses they are, and the physics around that. But yeah, if they did, we'd find out about it with gravitational waves. Yeah.
And back to the rover again. How many universities actually compete?
Quite a few. So the Australian Rover Challenge has gotten quite big lately. I know there's quite a few Melbourne unis, like Melbourne Uni, Monash, I think RMIT, Swinburne have some, and then that's held in Adelaide at Adelaide Uni. So lots of people go there. And then we also got, I think people from Germany came there as well. So that was really cool. But the one in Utah, they actually cap it. So there's like a selection before you even get to go there. So you submit your proposal of what your rover's going to look like, and then pretty much they eliminate teams off that, and then then you actually get to go.
And all the rovers have the exact same samples each, do they, to try and analyse, right?
Yeah, I think now they've updated how it works from when I was last on the team. That is actually just open range, so you've got to try and justify why you've picked a certain site to grab a sample of, which is probably more like real life then, because you've got to go, oh, I want to pick there because there's a crack in the ground, so there could have been water, so there might be more likely to be life there. So yeah, everyone's got the same tasks to do. Yeah.
Okay, any other questions? Oh, well, with that, please thank Jennifer for a lovely talk.
Thank you.
And while you're here, we have a little gift for you. And we'll also offer you and your partner a complimentary family membership for next year as well, for coming out and speaking to us. It was a very articulate talk, very articulate. Good luck with your PhD.
427 days into what should have been a 30-day mission, and it's turned into a nightmare. On the surface of Mars, 297 million kilometers away, is Ingenuity, a tiny 680-gram helicopter. It's made from off-the-shelf parts you'd find at home. It's got bits from an Android smartphone, batteries from a cordless drill, and to everyone's surprise, it's been performing well so far. But something is wrong. See, the Martian winter is coming. At night, temperatures plummet to a frigid -85 degrees Celsius. As Mars gets further away from the sun, the temperature keeps dropping, and it kicks up more and more violent dust. The sun is blotted from the sky. On her 427th day on Mars, they try to reach her, just like the day before. But they get no response. They try again, nothing. Back on Earth, the team gathers at the Jet Propulsion Laboratory in Southern California. All the signs point to Ingenuity being dead. But there is still one thing, one final trick they can try to re-establish a connection. The first drone that's gonna fly on another planet. 6 years ago, I visited JPL and saw Ingenuity before she left for Mars. At the time, NASA didn't really believe much in her mission. As Kenneth Farley, the project scientist of the Mars 2020 Perseverance mission, said, "I've personally been opposed to it. Spending 30 days working on a technology demonstration does not further the goals directly from the science point of view." In short, they thought it was a waste of time. Most projects to Mars get billions of dollars. Ingenuity got only 80 million, which is less than the budget of the movie The Martian. But this scrappy team of scientists were working to prove a crazy concept. And against the odds, they made it to Mars. On February 18th, 2021, the Perseverance rover survives entry and lands on the Martian surface. Attached underneath is Ingenuity. This marks Sol 0, her first day on Mars. They sever the umbilical cord, and Ingenuity, affectionately known as Ginny by some on the team, prepares herself. Her mission is simple: prove that flight on the Red Planet is possible. But with an atmosphere just 1% that of Earth, flying is really difficult. She must be ultralight, and her blades must spin at over 2,400 rotations per minute to generate enough lift. It's a design that no one is really sure about. For 2 months, they rigorously check her systems, running up the engine, testing navigation, and her control computer. Then, on Sol 58, they finally think they're ready. The blades spin up, and she takes off. Only 120 years after the Wright brothers on Earth, humanity flies on another planet. Within days, they fly again, and then again, and again. In just 1 month, they complete 5 flights. So the mission has been accomplished.
We were a tech demo, right? Meaning a specified narrow 30 sol mission, get in, get out, we're done, right? We go to a bar and party and that should be the end of it.
But with success comes new expectations. NASA tells them to keep going. Ingenuity's new mission is to assist Perseverance in the search for evidence of ancient life on Mars. So she will scout ahead, gathering data in areas too risky or costly for the rover to explore. For the team, this is great news, but it's also a problem.
There was no guarantee, after Flight 5, we may be dead by Flight 7, right? We may be dead by Flight 10.
We were kind of thrown into the deep end of the pool. We had no processes or no plans developed for such a thing.
Until now, every flight had been carefully planned. They've all started from an area selected and analyzed by both satellites and the Perseverance rover itself. These flights were tested hundreds of times in JPL's wind tunnel and tens of thousands of times in simulation. But now that they have to keep up with the rover, they're flying into the unknown. Now, flying the helicopter isn't easy. At its closest, Mars is 56 million kilometers from Earth, which means there's at least a 6-minute round-trip communications time delay, which is way longer than Ingenuity's 2-minute maximum flight time, so she has to fly autonomously. So what happens is the pilot programs in a route and Ginny does the rest. But to start, JPL first needs to know exactly where she's located. You might think that they would use GPS, but for GPS to work on Earth, you need at least 24 satellites for full coverage. And around Mars, there are only 7 satellites total, so Ingenuity can't use this method. So instead, what she does is far simpler.
We have 2 cameras, a forward-facing 13 megapixel camera, and then the one pointing down is the one that we use to navigate.
The navigation camera takes 30 black and white images per second. Ingenuity's computer analyzes the image and identifies features on the surface.
You can think of it sort of like an optical mouse. Like your optical mouse is on the mouse pad. It doesn't know where on the mouse pad it is, but when you move to the right, it knows you move to the right. Because what it's doing is it's looking at features on the surface of the mouse pad and watching them move under its field of view. So Ingenuity is essentially doing the same thing. It's looking at the surface, it's picking out features like rocks and other things, and between camera images it says, oh, this rock moved this way, this thing over here moved this way, and from that you can compute a transform to say my helicopter was here and now it's here relative to this image.
Now this sounds good, but the method isn't 100% reliable. On Flight 6, the first time she leaves her testing area, Ingenuity detects an error. 54 seconds into the flight, she starts wobbling wildly, tilting 20 degrees at a time. Her emergency alarms blare.
We had black and white image, black and white image, black and white image, and we had a color image come very closely to where that black and white image occurred in time.
This color camera was added late in development, leaving little time for testing. And during this flight, one of the images arrives at the exact same moment as a black and white image. The system doesn't know what to do, so it drops the black and white image. This makes every following image one step behind. This means Ingenuity's cameras are giving her outdated information. So even when she's in the right spot, the computer thinks she's lagging behind and pushes her forward. So she overshoots, tilts too far, and then has to overcorrect in the other direction. This cycle repeats, making her wobble worse in a positive feedback loop. Now that is a problem, but it isn't fatal.
The desyncing issue was like 1 camera frame off. If it had been more than that, I think you can imagine that it might have death spiraled.
Instead, Ginny detects the problem and is able to emergency land before it gets too ugly. While safely on the ground, JPL discovers the error and quickly corrects it with a software patch. It's a close call, but they recover. Over the next dozen flights, they keep up with the rover and support the mission. That is, until Flight 19.
We were about to fly that 19th flight, and I got a phone call the afternoon before, basically saying there's a dust storm brewing near Jezero Crater. And so we quickly canceled the flight and said, well, we're just going to hunker down and see what happens.
They brace for impact. It lasts 6 days, with winds gusting up to 20 meters per second.
That first dust storm in the middle of fall, in the first Martian year that we were on the surface, it clobbered us.
But they make it through. Nervously, they try to make contact. And she survived. She hasn't died or toppled over, but now they have a new problem. Dust. Dust on Mars is no joke. I mean, for Ginny, there are 2 big problems. First, dust is covering her solar panels, reducing power by 18%. And second, it's clogging her mechanical components.
We went to go fly, and when we went to wiggle the servos, they were actually stuck. They were kind of jammed from the dust. So that aborted the first attempt at Flight 19.
Now, JPL had anticipated both of these problems, but they hadn't had the time or budget to fix them. So for the first, they just have to accept that they have reduced solar power, and they adjust their flight durations accordingly. For the second, they find a workaround by repeatedly wiggling the servos until the joints clear. So she's able to keep flying, albeit wounded. And survival isn't getting any easier. See, every Martian night, the temperature drops precipitously. My friend Alex from the channel Astrum describes it well.
With less atmosphere, Mars became far worse at retaining heat. When the surface starts to cool, there is no air to catch the escaping warmth. It is at the point where, if you were to stand on the planet's equator during its warmest time of the day, your feet might feel 23 degrees Celsius, while at your head, it would be 0 degrees Celsius. This means between day and night, Mars has some intense temperature swings. Temperatures there now range from highs of around 27 degrees Celsius down to a freezing minus 133 degrees Celsius at night.
If you want to learn more about how this leads to entire planet-covering dust storms, Astrom has a whole video on the Martian climate. So these massive shifts in temperature are happening all the time. But as Ginny's mission progresses, Mars gets farther away from the sun and enters the Martian winter. So it gets even colder at night, which is a problem. Many of Ingenuity's key electrical components are hand soldered, and big temperature swings cause expansion and contraction of this metal, and so that can eventually break these connections. Also, inside the batteries, a liquid electrolyte solution allows lithium ions to move between the cathode and anode during charging and discharging. But if this solution freezes, JPL fears that the whole thing will stop working entirely. So what they do is keep all the components sensitive to the cold inside a warm box, which has resistance heaters that run during the night.
You might spend 25 or 30% of your battery flying, and the other, 60 to 75% is all just staying warm at night.
The problem is, the colder it gets, the harder the heaters have to work. And if they can't keep up and the batteries cool too much, they become less efficient. So they supply even less power to the heaters. Performance can continue to degrade in a vicious death spiral. On the morning of May 3rd, the team at JPL goes about a normal day. They check the data from the previous downlink. Nothing. They try pinging Ingenuity. Still nothing. Have they finally lost her?
Did we just lose our $70 million helicopter on Mars? Is this the end of the mission?
We thought this was it, so let's just make sure before we close the door on Ingenuity, we've thought of everything.
We'll just keep working through it.
They run through all the possible problems until they narrow it down to just one. The way she was designed, Ginny has an alarm clock that wakes her up.
It stays awake for 15 minutes. If it doesn't hear anything after 15 minutes, it goes back to sleep, and it doesn't wake up until the next alarm.
Their hypothesis is this: if the lack of sunlight forced Ginny to fully deplete her batteries, then during the night her heaters would have stopped and she would have powered off completely. When the sun rises, as long as her essential components still function, she may recharge enough to wake up. Only now her clock will have reset. So they run the calculations. If she's still alive, based on when the sun comes up, she should be waking up at 11:45 a.m. Martian time. That is not the time they had been trying. So they change their search window and start calling out to Ginny around when they expect her to power up. They send out ping after ping until finally, she's alive. They check to see whether everything is still working. And despite the components in her warm box only being rated to negative 45 degrees, they survive being completely frozen. Well, all except for one. The inclinometer is dead. The inclinometer is what lets Ingenuity know her physical orientation in 3D space before flight. And that is pretty essential for getting the right heading.
You can imagine if you're off in heading by 10 degrees, you could fly into a mountain.
Without the inclinometer, there is no way for her to fly. So at first, the whole team is stumped. But then they have an idea, because Ingenuity is made of phone parts, literally parts from phones people carry around every day. Her processor is from a Samsung Galaxy S5, and some of her sensors are from a Google Pixel 3. And these phones can do a lot of the things that an inclinometer can do. Inside every smartphone are at least 3 little micro electromechanical systems aligned perpendicular to each other, like X, Y, Z. At their core is a small mass suspended by flexible arms. They work like springs and follow Hooke's law, F equals minus kx, where force is proportional to displacement. The mass also follows Newton's second law, F equals ma. If you combine these equations, you get A equals minus kx over m, which links acceleration and displacement. Surrounding the mass are fixed arms. When a voltage is applied to the mass and arms, they form a capacitor, where epsilon and A stay constant, but as the mass moves, the distance between them changes with x. This alters the capacitance, which becomes more noticeable with multiple plates, hence why they have so many little arms. By measuring capacitance, you can determine displacement, and since displacement is proportional to acceleration, changes in capacitance allow us to measure acceleration. That's why these devices are called accelerometers. And by integrating acceleration over time, you can work out velocity and then position. This is how motion tracking works for screen rotation, gaming controls, and step counting. If you add gyroscopes, you get an inertial measurement unit, or IMU, and Ingenuity has the same IMU as the Google Pixel 3. So the team at JPL had an idea. They could reprogram the computer to use the IMU to replace the inclinometer.
The inclinometer is really just accelerometers that allows us to tell the initial attitude of the vehicle in roll and pitch. And the IMU also has accelerometers, so in principle it gives you some information.
So from the clutches of failure, they get her running again.
We got lucky in that, like, the one instrument we could afford to lose was the one that died.
But the IMU isn't space grade. In fact, none of these off-the-shelf parts are, which means they're vulnerable to cosmic rays. On Mars, the thin atmosphere doesn't just make it harder to fly, it also means cosmic rays reach the surface more easily. And a single cosmic ray can strike a computer register and flip a bit inside the computer, which can lead to some strange behavior. It even happens here on Earth. It once added 4,096 unaccounted votes to a candidate in a Belgian election. Now, on a Martian helicopter, flipping the wrong bit at the wrong time could mean losing control and crashing. So why doesn't that happen?
If you asked somebody 10 years ago, can you fly just the latest cell phone processor? They'd be like, no, it'll last like 2 days and you'll be dead, right?
Turns out that cosmic ray bit flips are not as big a deal as NASA thought. The off-the-shelf components hold up way better than they expected. And this is an important finding.
Rather than going through all of the development cost of building up a processor from scratch to be radiation tolerant, what we're finding is you get a lot better bang for your buck by just going and basically buying batches of different processors and just qualing them. That means throw them through a radiation test campaign, look at the failure rates, and figuring out, hey, this guy, we don't know why, but for whatever reason, this processor over here is great. It holds up, so we'll fly that.
Now, using these surprisingly robust off-the-shelf parts, they survive the rest of the winter, but they're only barely able to stay within the communication range of the rover.
Springtime came,
yeah, exactly.
The birds were chirping on Mars. Yeah.
Talk about spring optimism, right? Like coming out of winter.
With the increased sunlight, they can now fully recharge and return to their scientific mission. Over the next 41 flights, they image craters Perseverance can't make it to. They capture stunning images of the Martian horizon from above. They conduct daring aerodynamic tests, and they begin to push the limits. They want to fly faster, but the faster they go, the quicker features move across the camera's field of view, and the vision navigation system just can't keep up with that. So JPL comes up with a solution. They fly higher. Then they can expand the field of view, which means features will move more slowly through frame. So from an initial goal of a 10-meter altitude, they go up to 24 meters. And as a result, they're able to go from flying at 2 meters per second all the way up to 10 meters per second.
We set speed records, distance records, altitude records, just everything we could think of to push that flight envelope on Ingenuity. Really make the most of this once-in-a-lifetime opportunity of having a helicopter on Mars.
Everything is going swimmingly. Ginny and Perseverance have made it all the way to Neretva Vallis, a river delta in Jezero Crater. But on Flight 71, there's a new problem, and it's worse than any of the ones that came before.
So we just had this one final thing to do. We needed to cross this sand dune and make it to Bright Angel to rendezvous with the rover. So on 71, we basically went up, we were flying, and then after about 10 seconds of flying with degraded navigation, we went into an emergency landing mode and sort of came down hard.
They hail Ginny, and luckily, she's still alive. In the error code, they discover the problem. as she was flying over the dunes, there just weren't enough rocks or landmarks for her camera to identify. And without those references, she quickly lost track of her position and had to make an emergency landing. It's similar to the camera issue from Flight 6, but this time there's no software fix. They check for structural damage, but surprisingly, everything is still intact. So they attempt another flight, this time going straight up to scan the surroundings and then coming straight back down. Simple.
We popped up, took pictures, and then on the way back down, we hit the same problems we did on 71.
Only this time, it's fatal. Perseverance drives over and captures this image of her crash site.
When we saw the blades broken, when we saw that first image after Flight 72, that was heart-wrenching. It was like, no, there's no way this mission's going to continue. That was very depressing. So why? Because 71 was also a crash landing for the same reasons. It was the nav system was confused and drove us into the ground, but we came out of that apparently unscathed, and yet on 72 we self-destructed.
This is the first air crash investigation on another planet, right?
Yeah, that's right. First aircraft on another planet, and then the first air crash investigation on another planet. Yeah, they kind of go hand in hand.
At the crash site, they find Ingenuity's blades scattered, but not in the way they expect.
We noticed something interesting, which was there was no blade strike spot. Blades spinning this fast, when they hit the ground, right, they're going to create a spray. There's going to be a pattern, probably even visible from orbit. And we didn't see anything like that.
So if the blades didn't strike the ground, then what happened?
So this is an actual prototype blade from the development phase. This is essentially identical to the blades on Ingenuity. It's a carbon fiber composite with a foam core. It's incredibly light if you want to feel it.
Yeah. Whoa, that's actually great. That's like at least a quarter of what I expected just looking at it.
It doesn't feel physical.
So why did they break? Well, as the blades spin, the tips of the blades trace out a circle, which you can think of like a hula hoop. If there's a force up on the near side, you might expect the rotor to tilt immediately in this direction. But that is not actually what happens. See, the blade isn't stationary, it's moving really fast. So when you apply this force, it actually only moves after that point. So the maximum displacement occurs 90 degrees later. So even though we push up on the near side, the blades tilt up on the right and down on the left. This effect is called precession, and it's the same principle that explains this spinning bike wheel demonstration. Now, Ingenuity has a second set of blades that are moving in the opposite direction, which means that when a force is applied, each set of blades experiences precession in the opposite direction. For the helicopter overall, these torques cancel out. But each individual blade still flexes because of that precession torque.
That results in a stress concentration right about here where that final reinforcement tapers off. And so if you had a precession-based failure, you'd expect it to fail right here. And sure enough, that's exactly where you see it in the pictures. You can see sort of this jaggy place where the blade tip just got ripped off.
So that is what happened on Flight 72. As Ginny came down hard, she hit a dune at an angle. The force was transmitted up through the body of the helicopter, and this created a precession torque that bent the rotors, and they snapped right where the reinforcement tapers down.
This thing came down hard. It didn't destroy the landing gear. It didn't break the avionics. It didn't kill the servos. The swash plates are all fine. They're all intact. It's the rotors. That's the weak link.
So that is the first thing they're changing on the next generation of Mars helicopter, which is called Chopper.
You had a chance to hold the Ingenuity blade. This is the next gen baby blade. It looks fairly similar with a couple of key differences.
They reinforced the blades to withstand the torques caused by hard landings. Now they also have 6 rotors instead of 2, which means Chopper can hold a lot, even carrying a scientific payload of its own.
We've developed now a very lightweight radio that can communicate directly to orbit.
Whoa.
So we're a free bird
That's
when it
huge.
comes to exploring
That's
the
huge
red planet now.
because you were sort of trying to trail Perseverance, right? Yeah. And now you can go anywhere.
Yep, we're our own spacecraft. In this blue box, you can shove about 5 kilograms of science payload and bring it anywhere on the planet on Mars. You can fly 3 kilometers per sol in a matter of minutes. That's really generated a lot of excitement in the science community. So this is a 5th scale model of chopper. It's really 2 systems. So this is our chopper platform, right? This is what's going to go on and explore the entire surface of Mars one day. That's the point of the concept. But underneath is a mid-air helicopter delivery platform.
See, Mars rovers all need complex sky cranes to land, but a helicopter is different. It just needs a platform to take off from.
So the idea is we come down through the atmosphere. We have this jetpack that we need to slow us down, to get us down to a regime that is controllable so that we can take off from that platform midair and land under our own power.
For this, it needs rockets.
3, 2, 1. Awesome. You're envisioning like a future of aviation all over Mars as a primary explorative capacity.
In my mind, it's absolutely going to happen. It's just a matter of time. There will be fleets flying, throughout Mars. There will be airports on Mars one day, and we'll have aircraft the size of Chopper, more aircraft the size of Ingenuity, and even bigger than Chopper.
NASA is thinking big thanks to Ingenuity, a project they once doubted. Because Ginny showed what is possible.
In 1890, if you had said, I'm going to fly, it's like, okay, that kooky guy in his garage, he thinks he can fly, he's going to kill himself, right? After the Wright brothers, it's like, oh, okay, yeah, this is a thing that we're going to do. And so that's the change in mentality that's occurred because of Ingenuity.
That's why, still sitting there on the surface of Mars, attached to the underside of Ingenuity, is a tiny scrap, 1 square centimeter of muslin fabric. It was taken from the lower left wing of the first airplane, the Wright Flyer. From the first flight on Earth to the first flight on another planet. From Ingenuity's grave on Mars, her spirit lives on. Except she isn't quite dead yet.
She's acting as a weather station now, capturing photos every day, capturing temperature measurements every day, something no one would have ever predicted before Flight 72, that if things don't go well, would you still have a functioning spacecraft? So she's a tank. The team couldn't be more proud of what Ingenuity's accomplished.
And with that, we'll close with a very short video that goes for about 2 minutes, showing all the NASA spacecraft and where they currently are in the solar system as of July. And you'll notice in the video the points L1 and L2, the two of the 5 Lagrange points of Sun-Earth. And these are points whereby spacecraft can actually orbit around, even though there's no mass in the middle. So pretty much like what the JWST does. And you'll actually notice it as they pan around, that you'll see the shape of the orbits orbiting around basically free space. So very, very clever. It's set to high in the sky by Alexei action. So lots of craft. They're the active ones. And with that, I'll close the meeting and we'll see you hopefully with the November meeting. Thank you, everyone.